Hmm. All right. Hello, everybody. My name is Mark Schnesk. I am, where is there? There we go. This is our webinar following up on our drone demo day. So my name is Mark Schnesk. I'm an application engineer with Seiler Design Solutions and Seiler Geodrones. I'm a civil infrastructure technical specialist in Autodesk Civil 3D and related Autodesk in AEC collection prod, programs, as well as providing tech support and services for customers on getting them trained on doing data processing. So everybody goes out, everybody sees these drones, they're flying, they're awesome. We're collecting all sorts of data. And I have one more person coming in. Hold on. Participants. Yeah, she's in there. There's Lauren. Okay. There's Lauren in here coming in to join us. We got a couple more panelists coming in as well. All right. So we see all this data these drones flown. We've seen the data collected. We're doing two different things. Typically for these aerial UAVs, we're collecting either photogrammetric data, taking photos of a site over a nadir site, or we're collecting LiDAR data, which is an active scan data. So with a variety of different too. So today we're going to say, okay, everybody's seen these drones fly at their drone demo days. Let's go through some processing options. What is it we're exactly going to get out of this data? Okay, so the introduction, we're going to talk about the data acquisition info, photogrammetry processing, photogrammetry results, what we're going to get out of that. We're going to talk about LiDAR processing and the LiDAR results. Why are we going to use photogrammetry over LiDAR? What we're going to get out of both of those in a similar situation. Also going to go from those data to post-processing. So once we get our data processed into a model, how do we extract data out of there to put together a nice CAD data and the CAD file from that data? So for the data for the demo, what I'm going to show today, most of it, but not all, I'm going to have to go through a couple files due to some technical issues. Um, most of the data we flowed that I'm going to show today was flown at the Beaumont Scout, not Scour, Scout, Scout Reservation. I'll have to fix that in post. Scout Reservation in High Ridge, Missouri. It's right near our office down. They've given us permission to fly their site all the time. It's got a variety of wooded areas, flat areas, buildings, and structures. We're going to talk about photogrammetry. We flew the photogrammetry with our DJI Mavic 3 Enterprise. So if you remember, that is our smaller drone with a fixed camera, both for inspection and photogrammetry, as well as the Wingtra 1 Gen 2. So we flew this with a fixed wing drone with that RGB 61 camera in there. It's a 61 megapixel full mechanical shutter camera used for flying very high and getting that data out of that. We also flew this with LiDAR, with the DJI Matrice M350 RTK and the DJI Zenmuse L2. So we'll compare that kind of LiDAR data to the Wingtra Gen 2 LiDAR. This is a Inertial Labs recipe, or no, it's the Inertial Labs recipe LiDAR, as well as DJI Matrice M300 with the GeoQ TrueView 660 LiDAR. This is our LiDAR system. So we kind of compare those data sets together. So photogrammetry, we're going to start with photogrammetry end of it first. Photogrammetry is the process of taking pictures of very high overlap. So photogrammetry is going to be able to create a model. It's a series of stereoscopic images. It's to be able to put together a 3D model, flying high, taking nadir images with a high overlap. So that means the 70 and 80% overlap and side lap means for when the drone is flying forward, it's only collecting 30% new data with each photo. And with each successive pass back and forth, it's only collecting 20% data. So a very dense mesh of data, photos that software can take advantage of. If you ever look through a ViewMaster or at stereoscopic images, you can see that 3D uh, parallax 3D stereoscopic view. So we have software that can do this over an entire network of photos to pull out very accurate data. It's ideal for landscape surfaces or areas without much vegetation. It's easy to make 3D models or digital twins for progress updates, engineering designs. One of the greatest benefits we can get out of photogrammetry is an overall orthometric photo. So we can get an ortho photo of the entire site meshed together from these. So if you're using it for CAD background work or just construction comparison, day 1 to day 2, this allows you to get an accurate orthometric photo of your site for design purposes instead of relying on something that you downloaded, that may be 3 to 5 years old. Accuracy for this data. So it is highly accurate. We can get up to 1 to 2 centimeters in the X and Y. So its accuracy depends on a factor called ground sampling distance. You'll hear this term thrown around, and I'll show you some average GSD values. For each pixel that a camera takes, we can estimate the size of an object in that pixel by a factor called GSD. So basically, in a nutshell, it's a factor of the focal length versus the distance away from an object, where we can estimate a nominal value for each square of a pixel. Typically, we're flying a site, depending on the camera. Let's say the DJI, this guy right here, the DJI P1 camera. It's a 35 millimeter, 45 megapixel camera at 260 feet. We can get about 1 centimeter nominal GSD on an average 8,000 by 5,000 pixel photo. So that means when we look at that photo and we zoom in, each pixel is an estimated 1 centimeter square. Nominal values we can get accuracy wise are 1 to 2 times that in the X and Y, and 2 to 4 times that in the Z value. Z value is always nebulous. Z is that elevation range. But you think of those values. The lower we fly, the lower that GSD number means, the higher accuracy. But we're also doubling the number of photos or tripling the number of photos. So there's a trade-off versus accuracy versus speed. The more photos we have, the longer exponentially it takes to process that data. The nice thing about photogrammetry too is we can use a variety of software. I'm going to show 2 or 3 in this webinar, but you can go out. There's literally dozens of different photogrammetry software that you can get to process this data. We're going to show things like Pix4D, Matic, or Survey, or Mapper, Trimble Business Center, Recap. Even Autodesk has a photogrammetry software. It's not the best out of the box, but it will certainly do if that's all I have. Out of that, we're going to get a 3D point cloud in the las file. Oops, still on there we go. So photogrammetry process, we can produce 3D topographic models, orthomosaic photos of site, building, or an object. We use a variety of software and can be used to extract 3D point feature and surface data from models using additional software. So your typical workflow is we collect the data, we capture it, we grab our photos, we plan our missions, and we're going to make sure that we get a certain area. It's going to collect photos over that site using those parameters we set, that 70 and 80%. So most of the firmware and the software used to collect the data will automatically plan the flight line and plan the trigger speeds to make sure we get those nominal values that we want for a site and overlap. Again, we can process this in a variety of software, and I'll demo 2 or 3 of these in an average. And through that feature extraction, we can export that out to CAD. Okay. So I'm going to stop here. I'm going to go into a demo mode. So I have a variety of software open. Just kind of show you the kind of data we're going to get out of here. So I'm going to log and go to my Beaumont folder. So I have a folder with all this data. We look at the data that was collected. Oops, there it is. We looked at the kind of data that was collected. So when we're flying a site, in this case, I'm going to show you data from the Mavic 3 Enterprise. we're going to get a folder that comes off of that that unit. All the data is typically collected, regardless of the system, whether it's Wingtra or DJI or TrueView, GeoQ. All that data is going to go to either a micro SD or a full-size SD card on that aircraft, typically on the payload. So the RGB61 camera in the Wingtra is a little full-size SD card. For the P1 camera, which is the DJI, it's going to be on a full-size SD. The Mavic 3 Enterprise, or sorry, the Mavic 3 Enterprise, the smaller drone, it's on a little micro SD. So you're going to go through, and the nice thing about it is it typically will put it in a folder for you. So each of these photos of this site was flown, depending on the camera, aperture size, the size of the CCD, the focal length, the altitude you're flying. You're going to get, whoops, we're going to have to quit that. Otherwise, it's going to bug up here. We're going to get a photo that's going to be, have some detail on there. So in this case, you're looking at a photo. This is the Mavic 3 Enterprise, probably flown at about 200 feet. So our average pixel size here is probably going to be roughly somewhere around 1.5 to centimeters per pixel. I'd say 1.5 centimeters per pixel. Which means each pixel on the photo. And you can see even from that altitude with a smaller moderate camera, we can get quite a bit of detail for each of these photos. So those photos are collected in, and each photo, by the way, will also contain metadata. So if we go to these properties on these photos and we dig into that metadata, they're going to either be tagged directly in the flight, or we can use, in the case of the Wingtra, we have to manually align the GNSS data. So it's collecting both in the IMU, the inertial measurement data, the GNSS data it's getting from satellites. It's going to post-process these together, either in the case of the Mavic or the Matrice, that is a real-time kinematic. It is writing exact data to the photo. Or in the case of the Wingtra, the GeoQ, we have to have a base station. We have to post-process that trajectory and then assign those photo points to the photos. But either way, for each of the photos, it's going to write in the header of that photo, in the metadata, its position in both latitude, longitude, and ellipsoid height altitude. Typically, photogrammetry is going to, so each of these photos, if I just put it onto a Google Earth map and bring it in, and tell it to read that geodata, it's going to be able to place this photo at the exact location that it was taken. There's additional data you can't see here that the properties viewer in Windows doesn't show you all the metadata. There's kind of like fixed fields that it does show you, but you can go in further. There's some websites that allow you to really read into the EXIF data of these photos, and you'll see things like the drone IMU data, its position, not only its position in the sky, but its pitch, roll, and yaw axis at the time the photo was taken. And different photogrammetry software can take advantage of not only the camera tilts, but the rotation of the drone to not only accurate position at X, Y, and Z, but also in the right rotation orientation. And all this software could take advantage of that. So processing, I'm going to show you quick processing through a typical processing. So this is additional data brought in. This is going to be a little lighter weight, but if I was going to bring that, so I'm going to show you one of the methods. And I'm going to introduce you to Pix4D-Matic. It is just one method of doing it. I will show you another method using Trimble Business Center, and I will show maybe another method using another software. But just to kind of show you, no matter what software you use for processing photogrammetry, it's basically handled the same way. We're going to import that data in. The software is going to read the XY position of that photo and arrange them in a matrix within real world coordinates. We're going to calibrate those images. So those images get calibrated in. It creates a lightweight model based upon the 3D stereoscopic mesh it sees. Then we're going to go and say, okay, this is good. We're going to apply ground control, and something I haven't really touched on yet, but we're going to get good data from the RTK. Matter of fact, we're going to get stellar data from RTK or post-processed positions, but things could go wrong, and we could get even better if we have proofed ground control. These are 3D points we've shot in the ground. We can really tie that data in in a very precise way. So to start a typical project, different software work different ways. Pix4D-Matic, this is just one example. So it says drag and drop, or you can select folders. I'm just going to select a quick folder. I'm going to go to, we'll do something easy. So I got some Wingtra data. The reason I'm going to show this is, well, we do look at the Mavic Enterprise stuff. Let's look at that. Okay, here's that folder of data. I'm going to select that folder. I'm just going to throw this on my desktop and give this a demo. M3E is the name of my project. Different software run in different ways. So right now it's reading those images. There's 846 different RGB images that it's bringing in. Once that's done, you can see how it's arranged those photos. So this is the typical pattern that I've flown. Each blue dot here represents a photo that was taken. Your typical software is also going to be able to show you those photos in either a plan view or an individual view, depending on the software. Trimble Business Center doesn't show you the photos here, but it shows you the photos in the plan view in XYZ, which I can show you that as well. We have our images, then we're going to, the first thing we do, no matter what, remember our photos are in latitude, longitude, and ellipsoid height in meters. The next thing we're going to do is we're going to set our export coordinate system. So we're going to select our coordinate system out. This was done in Missouri. I can choose a variety of different state plane or projected coordinate system. Most software is going to have projected coordinate systems, even down to the county level. If you're live in a state like Indiana or Wisconsin, you'll have the county systems. I don't think the new Illinois 33 zones are in most of the software yet. There are a couple that do have that added. The nice thing about it is we can also import CRS files. If we don't have the exact coordinate reference system we're looking for, can import in typically as an Esri PRJ file. Sometimes you can create your nodes with a world WKT file. There is a website you can go to called EPSG.io. That's EPSG.io, and you can look up basically any external or projected coordinate system in the world and get the data, the metadata from it to create your own. If your software doesn't have it. In this case, I'm just going to choose the FIPS 2401 Missouri State Plane East. And also I need a vertical coordinate system because it is an ellipsoid height. That is a metric data. We're also going to convert this to the North American vertical datum of 1988 US feet and choose a geoid model that will be accurately reflected in that. When we hit apply, it quickly re-racks the photos and re-racks the projection. You notice things really didn't change much. Even though we didn't set one before, it was in a UTM metric coordinate system. So at this point now, I have my cameras. What I would do is there are a variety of tools. Typically, the software is going to process in the same way. There's a calibration stage. The calibration stage creates a complex network. It's going to create a lightweight LAS file based on a variety of parameters. When we go through training on these individual softwares, every software does a little bit different. There's some additional tweaks in the Pix4D that we can use depending on the type of scene that we have. Flat, low texture is going to be something like for open farm field. Map is going to be for a small finite space. Large texture and large scale and corridor is for basically greater than 1,000 photos, and it has a different algorithm it uses. We set our seed and we run our calibration. And once that's done, then we're going to come back and tie to our control. So I've done it with a different site. I don't think I did. Maybe I did it. Let me open that one up. Let me open the one that I have done here because I believe, yes, I did have it done already. It's got to take a second to open it. Maybe. There it is. So this is that same flight once it's processed. So we've run through, but first, after we run our calibration, the next thing we're going to do here is apply our ground control. So as I stated, you're going to want ground control items in there for photogrammetry. And ground control is going to be a 3D target that has been painted, or you've used applied a cloth target that's been staked down, or we have automated targets like the arrow points, which have a GNSS receiver in them. So as you set them out on site, they're a checkerboard square. It's collecting data. You post-process that, you get an XYZ file. But basically, you're going to have your points. And typically they're going to spread out in a better pattern. For a pattern like this, typically you're going to have it in the four corners in the middle, but this was just for demo, so they're a little bit closer to what I'd like. 3 to 5, even up for a 100-acre site, no more than 10 max. Anything beyond that, and you start losing your time versus your accuracy. It doesn't really matter. It's a lost what is it, the value of diminishing point of diminishing returns. Okay, for each of these coordinates, as I look at them, you can kind of see, and I'm going to mark these in my photo. So here's a typical target. We've applied that accuracy. So the blue represents the guessed position. The green is the finished position. The yellow is the mark. So as I mark these photos, a lot of software are going to have an automatic marketing. Some don't. But basically, with an RTK or post process, they should be pretty darn close. We're just nudging it that last 2 or 3 feet. But if I didn't have an RTK or didn't have post processing, ground control is the only way I'm going to get my final transition on that point cloud to its position. We run these, we get an initial positional error, we recalibrate that, it shifts the point cloud over to where it needs to be. After that's done, then we get our derivative data. So whether I'm using Trimble Business Center or Pix4D Matic or Pix4D Survey or a variety of other projects, it's basically the same. Once you've calibrated and you've moved your project to the right coordinate system, everything else is derivative data. If we don't have the calibrated data done right, the derivative data is going to be junk, and then we just have to start all over again. So we've gone through and made a dense point cloud, a mesh, and a digital surface model. So if looking at the data here, once everything's been processed through, I'm going to go through some layers and turn off my cameras and turn off my ground control so you can kind of see what we've got here. In my 2D view, then I end up with an overall orthomosaic. So here's an orthomosaic map of the site. It is the latest and greatest of the time we flew it. You can see I had a base station out. There's where my target is. So with that 1.5 centimeter per pixel camera, if I go here to my report, you can see the average ground sampling distance was about 0.05 of a foot. So each pixel is about 0.05, 0.05 feet. But you can see I get my orthomosaic. I can see curb lines. I could even just use this for plain 2D planning or orthometric CAD background as I draw over top of it. But I also get a 3D model. So with that, everything said and done, you're going to get a 3D point cloud. Now, 3D point cloud, you're going to see the weakness in photogrammetry. Photogrammetry doesn't penetrate vegetation very well. We get a nice point cloud here on the open grass. There is a target right there. We get a nice point cloud in the parking lot. And this point cloud is basically, it's a series of 3D or 2D points put together. I'll go ahead in my settings here and I'll turn down that point size so you can see individual points. So it's just this network of points that get extracted from that 3D photogrammetry. We'll turn off the automatic high points. There we go. So this is my final densified point cloud. I can export this out as a LAZ or LAS file and then take it to any software that I want if I'm going to post-process it. With the Pix4D world, there are additional tools that I can use that are attached to it. One of them is called Pix4D Survey, and I'll bring you into that to show you that workflow. Just to kind of show you the differences between the cameras. So for that Mavic 3 Enterprise, it is a 20 megapixel camera. So turning these cameras back on, go back to the 2D view. Turning those cameras back on, you can see we took 846 pictures to make this 3D model. But I have another one here, the Wingtra. So the Wingtra is that fixed wing with a 61 megapixel camera. I only have 134 photos for the same resolution. The downside is because I have less of a network, in order to get data further out, I'm going to have to basically increase. I should have increased my area of flight to be able to make sure I can get this data out here. Another thing with photogrammetry, like I said, is it doesn't collect data um, in wooded areas very well, especially if it's a windy or breezy day and the trees are moving. Photogrammetry relies on individual photos looking the same from one to the next. But still, for the same thing, for that same altitude, this is a 61 megapixel camera. For that same flight, this was flown at 400 feet, which is why I have less photos, 61 megapixels and 400 feet. For that same report, I'm just about a hundredth over, so 0.6, 0.7, 0.07 feet per pixel. So a little less resolution, but a lot easier and a lot faster to fly. And the same thing, I'm going to get a 2D and I'm going to get a 3D map. And again, you see that weakness. Let me turn off this mesh. Actually, I'm looking at the mesh model. Turn off the mesh and turn on the dense point cloud. There it is, the dense point cloud. So with any photogrammetry, whenever you have a thick canopy, you're not going to get, if I try to look underneath the trees here, you're not going to get any ground data beneath those trees. And this is where LiDAR is going to come into play instead. There's some trees there. Again, typically you're going to end up with a big hole, regardless of which model. Here's the Mavic 3 Enterprise one. And even though I get dense because I have a denser point cloud, when it comes to being under the trees, I'm going to get no data, and that's where I'm going to get the LiDAR. Okay. So let me switch over to LiDAR here really quick, and we'll come back to post-processing. So LiDAR, and then the other hand, go back to there we go. Light detection and ranging measures distances and reflectivity via hundreds of thousands of laser pulses. So it's an active light source scanner. Photogrammetry is based on a camera photo. It's dependent on the ambient light. If I have bad lighting conditions, fog or mist or harsh shadows, my photos are going to miss data or misinterpret data because it can't see the contrast between point A and point B, and it can't penetrate through that foliage. Whereas LiDAR, I could fly a LiDAR mission in the dead of midnight and still get full resolution data both above and below that canopy. I just won't have colorized photo. It has the ability to, I shouldn't say puncture. I'm going to change that. A punch through maybe, penetrate through vegetation. It's not actually burning a hole through the leaves. It's looking through the little interspatial distances between those leaves, that those holes. As you stand below in the ground canopy, you look up at the sky, you can see the blue sky through the holes in the leaves. This is the same thing in reverse. It's finding those little nooks and crannies to get that laser light down. Decreased cost and accuracy. The LiDARs have been coming down in price, and we're going to get a fixed, unlike photogrammetry, where the altitude determines the size of the photo and the accuracy from a model. LiDAR has typically a fixed accuracy, 1 to 6 centimeters, depending on the cost and the price of the sensor. So we have more expensive things like the Regal LiDAR in the GeoQ 660 or 720 versus the lower cost Wingtra LiDAR or L2 LiDAR. But still going to get accurate data and easy to inspect maps. And the other thing that photogrammetry does fail at is complex structural elements like things like substations or transmission tower framework, thin wires. LiDAR is going to be able to pick up that more complex structure. The downside with LiDAR is it requires proprietary software. Some of this proprietary software, they do charge you a subscription for just to have. Others just come part and parcel with the system. So it depends on the system you get. A lot of these LiDARs are just off-the-shelf parts, but we can use the firmware that's been developed in it to collect and create that 3D point cloud, and it's going to require that proprietary software. But once that's done, you're going to create the same thing you got for photogrammetry. You're going to get an LAS or an LZ file, and then we could take that just like we would the photogrammetry to anywhere we want. It can be used to extract 3D point feature and surface data from models. using additional software. So similar workflow to what I just presented with the photogrammetry, capture the data, use the proprietary, in this case, we have things like GeoQ. If our TrueView 660 is going to require the GeoQ LP360 software, DJI L2 is going to require the DJI Terra Pro, and Wingtro LiDAR has its own Inertial Labs Wingtro LiDAR app. So we're going to go through there. However, once we're done, we can take this to any software we want to process and create our Civil 3D CAD drawing. So the data extraction, we're going to post-process LAZ to DEM. Oh, actually, we'll get back to that. So let's go through the LiDAR demo. I have a couple of LiDAR scans here. So we flew the site with the same site with the DJI L2. In similar fashion, the data files you're going to get out of this, you're going to get similar to what you want the photogrammetry. Let's see, where is that? That is going to be. So if I go back to that and I go to the DJI L2, you're going to get similar data. You're going to get some photos. You're going to get some. Oops, there it is. You're going to get some photos. You're going to get the photos for the LiDAR for the L2 are strictly there for colorizing the point cloud. Both the L2 and the TrueView series, so the GeoQ TrueView 660, 535, 540, as it's collecting LiDAR data, is also collecting photogrammetry that's going to be used in the software to colorize the point cloud. Other LiDARs, like the Wingtra LiDAR, does not have a camera on board for it, so the LiDAR is going to be black. No, it's going to be colorless, but we can view these point clouds in a variety of other. One of the other things that we get from LiDAR that we do not get from photogrammetry is an intensity. As the LiDAR ray goes out, it bounces off an object, and a certain percentage of that energy comes back to the camera, and different materials are going to bounce back different amounts of light, so we can view these LiDARs in different intensity values. You're also going to get the actual IMU and data. So the same thing like the DJI L2 requires an RTK, or we can also post-process this. Other data like the Wingtra GeoQ requires you have a static base station logging data on site, or I could use something like CORS data or a virtual reference network OBS file, but there's going to be post-processing of that trajectory involved. So for the L2, what we're going to get out of it is we're going to get a colorized point cloud. This is that same site flown with the L2 camera. This is the DJI L2 LiDAR. As you can see, as we zoom in, just like we got from photogrammetry, we're going to get a point cloud. This is an LIS data that would come out. Unlike photogrammetry, as I said, we're going to get reflectivity. So we can look at these point clouds in a reflectivity mode. Colorization is nice when it comes to LiDAR. It lets us visually pleasing to the eye. We as human beings see, mostly see in color. We can see, we can identify, oh, look, this is a driveway, this is grass, this is sidewalk. But the problem with the colorization is it is a projected photo stamped on the LiDAR at the time it was taken. It could have been a photo in a nadir view like this, or we could have been over here and we're doing an oblique. I've seen a lot of times like they notice this tree is partly colorized to look like pavement because that was the photo that was used at the time of collection. So it'll apply some kind of false colors to some items depending on what you're looking at. Usually pavement markings and things like this are fairly accurate, but other items like 3D objects, you're going to get this false color. Heck, I've seen some oblique stuff where you're looking at trees and they're all colored sky blue because that's the color photo that it made when it did that. But when I look at an object in reflectivity, there is only one way to look at this. What you see is what you get. So here I could easily see where the curb line is from the grass line, and it's true in 3D position. That point reflected that energy at the time it was collected, and it's highly accurate. Typically, we can look at these as a height model as well. Most software has the ability to look at things through these different lenses so you can see what's going on. The height model here in Terra, DJI Terra, gives you a sense of how the landfall is going. I can see where my high land is versus where my potential drainage or flooded areas are in this. The other thing I like using for the returns is, unlike photogrammetry, that LiDAR light has penetrated through the interspatial distances between those leaves to be able to get data from the ground. I can easily see that hey, look, did you know there was a hidden creek there? There's no way for me to see that with photogrammetry because tree landforms have, or the tree forms have blocked that LiDAR or blocked that imagery or that data. So LiDAR lets us penetrate through those wooded areas. And you can see we talk about LiDAR having multiple returns uh, as you as the LiDAR light from the drone exits the vehicle, it's going to diverge to a small cone like this. And as it bounces off of it, different objects it detects, that light comes back as a fractional bounce back. So one single light beam can get multiple objects down. Those are called returns. Certain LiDAR, like the DJI L1, can track up to 3 returns. Certain ones like the TrueView 660 and the DJI L2 can get up to 5 returns. And there's a lot of software that says, hey, when I'm digging for ground, we're going to look at those last returns and prioritize those over other returns. Another aspect of point clouds that we didn't talk about too was that it can be classified in a type. The DJI Terra software has a utility when we're processing to extract the ground, quote, quote, from not ground data. So it's using standard, what we call ASPRS, the American Society of Photogrammetry, remote sensing specialists. They have a standardized classification that we can use. Class 2 is ground, and typically that's what we want. As in the infrastructure world, I'm flying a site, I'm really looking for ground topo data. Okay, I want to be able to take out the trees, take out the buildings, and get other objects in there. And this software, as it's processing, uses the statistical ground classification tool to pull that data out. So your typical setup for this is similar to photogrammetry. I drag my data in. If I was to start a new project here, new mission, I'm going to drag my data in. I'm just going to say new point cloud. I'm going to drag in a point cloud site. So this was the scan data, Beaumont, DJI L2. Oops, wrong one. There it is. Drag this folder in. It gives me the base position. This is where we had our RT or our OBS file set in. I'm going to set some things like density values. Maybe I don't want 100% of the points coming in. Maybe I only want 25 or 50%. So I can set up a percentage. Like photogrammetry, I have to set an output coordinate system. So everything is collected using GNSS data in WGS84 lat and lon. I'm going to need to set an output coordinate system like Missouri East and NAVD88 height. I can apply ground control just like I did in photogrammetry. Certain software allow it, some don't. DJI Terra and LP360 allow you to add ground control in. For DJI Terra, it will give you just basically as a checkpoint. Once it creates the point cloud, it will tell you the elevation difference between your point cloud average elevation at the XY versus the control point and give you a residual report. Or I can do a best fit vertical adjustment. So it may raise or lower the point cloud to best fit those points. Something like LP360, on the other hand, can do a full 3D transformation, rotate, and scale based upon your control points. And you'd pick them out just like you would ground control in photogrammetry. But I can add those points in, and then once done, I just basically set up my control here. Here's my ground point classification. I can opt to smooth the point cloud. What the smoothing does with LiDAR is a very noisy animal. You're going to get a band of buzz in there. You have algorithms in here to smooth that, to get to that middle third to 2/3 data in the center, your average elevation, and pull that data out. But certain algorithms like DJI Terra will end up rounding out sharp objects like curb and gutter. So you have to be careful of using that kind of tool. There are alternative methods you can use as well on like something like LP360, which would be ancillary software. I'll cover that next year and show you what we can do with that. But you can smooth or optimize your data, and then when you hit start processing, it's processed it through. So going back to that LiDAR data that I had open here, where is it? Beaumont. Once that's done, boom, you get your point cloud with all the data. Certain software like Terra also let you do something similar, like, okay, I can cut a profile. If I start and just say, what does this curb line look like? There is a cut, maybe. One, there it is. So there's my data from that cross section. So what I'm doing is I'm making a profile view in this scene right here, looking in this direction. That's a zero point 0.1 feet wide. So in the plan view here, I can zoom in and see my point cloud. And so what you're seeing is basically in that stretch. Maybe I'll make it a little bit bigger here. Maybe we'll go 0.5. There we go. Little thicker section, a little meatier there, kind of gives us a better feel of what's going on. But there you can see that noise band. There's my top of pavement coming in this way. There's my curb, and then there's my slope going off the back. So there is this noise. What the smoothing data would do is kind of, again, it would give you a thinner section, but it would end up rounding out this curve a little more. So you lose detail, you gain detail. It's all depending on what you want out of it. Okay. Um, Something similar like another proprietary software would be the LP360. So this is the tree view. This is that same site flown with the GeoQ LiDAR, which is a Regal-based LiDAR system. It's a little different, but basically the same. Unlike the L2, where the telemetry data is built into the system. All I have to do is drag the data and run it. The GeoQ is a little more intense. I have to do this basically step by step. So I end up getting a raw data. If I look at the raw data, it's kind of hard to see that green line there. Let me make it a little bit bigger so you can see it. We'll bring the thickness up to it. Okay. So this green line here is the raw data, how the mission was flown for each different flight. So this is like one flight. I had a battery change between flight 1 and flight 2. So it's showing my raw trajectory. I go through and create a complete finished trajectory, get rid of any of the ancillary lines that I don't want in trajectory, and then I apply the LiDAR to just those trajectory. The blue dots, it also collected photos as it was flying, so the blue dots represent the photos that were taken. This software works a little bit differently. It's not as intuitive as the DJI, but it's more powerful. And basically what I'm doing is I'm processing the trajectory. I'm combining my 3D trajectory with the base data and then getting a post-processed SBET, smooth best estimated trajectory that merges the GNSS versus the IMU, gives me a better product. And then it creates those flight lines in geocode. One other thing I could do is do what's called strip aligning. So with each of these flights, the different colors here represent the different flight lines that were made. Okay. So the strip adjustment, what it does is it will merge those strips together. Oops. Back to RGB. It'll merge those strips together. So for each flight line going this way, there may be subtle differences in the overlap area, that edge to edge elevation. And the strip alignment software lets me go ahead and merge and register each aligned together to get a solid. DJI Terra does it by that optimization tool that's in there. Just like the Terra, I can also apply control points to my data and then use that to get a translation and rotation. And out of this, I'm going to get an LAZ or LAS file, which I can also post-process. Projects like LP360 also have some built-in tools to do like point cloud tasks, to do things like extract building, extract vegetation, and extract items. They all kind of work. This works more on a statistical method. I did do some classification in here, so you can see the brown areas are classified. Let me turn this so you can see it a little bit better. The brown areas are ground classified. The non-brown areas are classified. I have a little cleanup on aisle 6 here to do, so I classified a portion of this building as ground. So in my classification tools here, I would use that to clean it up. For each of these products, if anybody at the end of the webinar, we can take questions. If anybody wants to see a demonstration on a particular piece of software, it's a lot to encompass in an hour. We can do a deep dive into a particular piece of software. I might offer some webinars later on that go into each piece of software step by step. Still, out of this, we're going to get an LAS file. So when we're exporting out, we're getting a LAS file. We can get some ortho photos out of this. We can also use this to process some basic photogrammetry. So once we've done LiDAR, once we've done our photogrammetry, regardless, and by the way, Trimble Business Center, also an amazing program to run photogrammetry on as well. This is a photogrammetry site. This is that same site you saw me do here in Pix40 Matic. This is that, sorry, there it is. This is that Wingtra RGB61 photogrammetry site. Trimble Business Center is an excellent source. If you are already a Trimble Business Center customer, getting that photogrammetry module in here will let you easily process. In the same way I did it in Pix, I do the same thing. I import my mission data. I post-process if need be, or I could just, if it's an RTK drone, I can just adjust and add ground control points. So here I have those same ground control points in there. I'd use that to adjust the model. So again, you're processing, you follow from left to right, you process, adjust roughly, then you adjust to your photo station, and then you're going to create your deliverables. And what are those deliverables? Well, in the 3D view, it's going to be a 3D point cloud, LAS. Let me turn off some of that photogrammetry issue. You're going to get that 3D LAS point cloud. In the 2D view, you're going to get an ortho mosaic. I have that on here. Maybe I didn't export an ortho mosaic for this one. Scans, field images, points. Apparently, I didn't do an ortho on this one. I thought I did. Data, photogrammetry, photo station, image, nope. Referenced, nope. Nope, I guess I didn't do an ortho photo on this one. So you can export one of your mission delivers. If I come here to my create deliverables, it's going to be something like, hey, I can do a medium quality mapping, either digital surface, and create a photogrammetry output as well. But once you get your LiDAR here in TBC, we're going to talk next about the final step here is the extraction. So extraction can use a variety of different products. There are one of them I like to use is, and we'll come back to TBC here really quick. One of them I like to use is Pix4D Survey. So in the Pix4D world, I could just say, hey, open a Pix4D Survey. Pix4D Survey is a program that allows you to add and extract data. So it's as simple as saying, I'm going to take this, open a Pix4D Survey. I'll make a new model here very quickly. We'll call it survey. So this basically would take all the data directly from what I collected in Pix4D Matic, bring it over to Pix4D Survey. There I've got my point cloud. And what I'm going to do out of this tool is, clean up my data, extract ground from not ground. So whether it's photogrammetry or LiDAR, I can just click a quick filter button here. It's going to go through my project. It's going to use a statistical based program to where you see what's in yellow is terrain or ground data. What's in blue is the not ground data. So if I come here to my layers and I say, hey, let's turn off the not ground data, I can see it's extracted what I want for surface data. From here, then I can go through and extract a grid of points. The worst thing you can do is take this last file, drop it directly into Autodesk Recap, bring that to Civil 3D, or take that directly into MicroStation and try to create a surface out of 100% of the, I don't know, what do we got here? 100% of the 14 million points that I see and try to make a surface, because it's going to crash the system. There's going to be issues with the surface. And your computer's going to struggle and possibly crash every 5 minutes or so. So what we're going to do is we're going to subsample. Once we get our ground down, we have a variety of tools here. In Pix4D Survey, we're just doing a standard grid of points. In Trimble Business Center, once I have my point cloud selected, I have tools here in the point cloud processing to extract the same thing. I'm going to make a random, I'm going to select this ground classified data, and I can extract a random number of points, and it's going to pull out those points in a grid type fashion. Once I get that data out, Then I'm going to go ahead and create a tin surface from that. So say, yep, well, I'm going to make a tin from the grid of points. There we go. So now I get a 3D surface directly from those grid of points, and I can go ahead and then create my contour lines. If that's all I wanted to, there we go. I got a point, I got a surface, I have a grid of points. Now I got some cleanup to do. Obviously, this is bunkus data over here. Really, I have very little data. Does this do this from here to there? No. Once I come into something like Simple 3D, I can use a trim to trim out those data that aren't there. If I have better data, let's see, I have another one here. It's open. If I have a better, more dense, yeah, there we go. If I have a more dense, this is that Mavic 3 Enterprise stuff, then I have a little better chance at getting that ground data. One other nice thing about these types of software, whether it's Pix4D or TBC, is I can bring in multiple sets of data. As I said, with the 3D data here in TBC, I can't see below the tree line in the photogrammetry. The same thing with Pix4D Matic. Whether I'm running this one or running the Mavic 3 Enterprise, I'm not getting the data underneath the tree line. Well, lucky for me, we also collected this with that LiDAR, right? So if you collect your data with both photogrammetry and LiDAR, then as tools like Pix4D or in Trimble Business Center, I can add both point clouds. So in this particular model, I have both the photogrammetry and the LiDAR in there. So with photogrammetry turned off, go to my layers, with the LiDAR turned off, you can see what I've done. I have turn off those contours and contour lines and grid of points. So I said, okay, I've gone ahead and I took my full-on photogrammetry and I drew. There's a tool in here to select. I just selected a bunch of data here and said, oh, by the way, delete this. Hit delete off my keyboard, and that removed that data out. Right. Then bring it back in. Then I did the opposite. I brought in the LiDAR data, and I did the opposite. I trimmed out the same area that the photogrammetry was in, and now I get the added benefit with this type of data here. I get ground data and top surface data. So I'm combining these two types of resources into one single area where I have good coverage with the flat areas and the open space. I'm going to prefer my photogrammetry because it's more accurate, but to get that penetration through the wooded areas, I'm going to use the LiDAR. And with the different tools, whether it's Trimble Business Center or Autodesk Recap or Pix4D Survey, I can control what I see through layering for each of the point clouds here. I can look at whether I want to see it in the full terrain class or as the ASPRS classes, turn on and off classes that I don't want to see. So there's the non-ground turned off. Where here's the non-terrain that was turned off. So I have a grid of points. We turn off both these point clouds. So I have two grids of points. I got a grid of points made from the photogrammetry of the ground. I've got a grid of points made from the LiDAR ground classified data. And then I'm going to make an overall tin of that site based upon that grid. And my contours are going to follow suit when I do that. So now I have a more accurate model that combines the best of both LiDAR and photogrammetry. One more thing we're going to do with this extraction is there's the ability to extract what's called layer data or linear and point data. Both Pix4D and Trimble Business Center have tools under there for extracting point features, linear features, extracting geometry. Even Recap has the ability to extract. If you're interested, I have a video on our blog source for classifying and extracting data using just Autodesk Recap Pro and LiDAR. I'll send out a message in the follow-up email. I'll send out a link to these videos if you're interested more, as well as this recording. But there are tools in here for like extracting curb lines. And extracting curb lines, you basically say, I'm going to extract the line feature here. You're going to create a particular section of the data you want to sample. In this case, it's going to make a section line between those 2 points. And it's going to, as it brings up my 3D view, there it is. It's going to bring up a 3D view. It's going to tell me the direction it's going to go. Here, I'm going to switch direction so it's pointing in the opposite side. And then basically, I'm going to build a 3D type of line. I want to extract the top, back, top, and then the ground data of that curve. And then giving it an interval. Let's do it in 3-foot increments with a 85 or 80% degree of confidence. And I'm going to say start extract. And what it's going to do is every 3 feet, it's going to start running that tool and extracting data. It's kind of hard to see because it zooms you way out, but you can see it running along, extracting those curved lines based upon that cross section. We'll stop it. We'll say finish. There's those 3 lines extracted in 3D, and then I can just say create those lines, and it creates them as 3D polylines in my 3D view. Okay. So fairly easy to do, and then I can add these to my surface as a break line or whatever. In Pix4D Survey, it's not as intuitive. I basically have to draw the lines, but when I'm adding layers in here, as you can see, I have like an edge of pavement or back a curb layer. For each of the layers in here, I can determine whether or not that is going to be like a terrain layer or not a terrain layer. Once I turn this into a terrain layer, if I come back here and recreate my tin, then it adds it as a break line. If I recreate my contour lines, then the break lines are going to conform to that. And I could do top of ground, existing ground. I didn't extract the top of curb or anything like that, but I have ways to basically come in and turn off the point cloud. So you're going to be using these views where you're going to be showing the point cloud, not showing the point cloud, showing the tin, not showing the tin, being able to see those lines, to be able to extract these and do cross sections as well. I have profile views available in either of these to help me. There are some semi-automated tools in here as well for extracting things like volumes or stockpiles, feature lines and catenaries, road marking, pavement marking, roofs and wall detections to create 3D lines, points, and planes. Again, we're using the point cloud as the 3D digital twin to extract our data on. We're performing a survey in our office as opposed to performing that out in the field. In the end, everything we're going to get, whether you're using TVC and extraction or using Pix4D Survey to extract, these all export out in both of them. In Trimble Business Center, we could extract the surface, the line work as CAD objects, as LandXML files, as Kogo points. Pix4D Survey, we're going to extract these lines out and points out and contours and surfaces as LandXMLs and points and CAD lines. And in the end, we're going to bring those into Civil 3D. So here's a Civil 3D drawing. It is basically a direct open of the DXF file you just saw. I can import that LandXML file in as well from that. Oops, did I not do a LandXML extra? Nope, I was in the wrong folder. Scan data, Beaumont. That was the Mavic 3 Enterprise survey exports. There's my XML file. So I'm going to bring in that surface as a Civil 3D tin surface as well. I can use that contour that's there, or I can turn on the CAD contours. But any of the surface that I just exported is there as this full Civil 3D surface. I can bring in the Kogo points from those features here. All these plus signs, the feature extracted grid of points. I can bring those in as Kogo point in the end to create my Civil 3D object. So it's fairly straightforward. You're just using the point cloud data as the basis. And if I have a couple errors here, I could either just fix it in here, or I can go back to the original source and fix it. It's a dealer's choice at that point at how you want to deal with it. But that's basically it. I think I had one full model extracted. Here's one. I'll show you one more model before we end the webinar. This is one I did for a site near our office. Let's see if I have it in here. Oh, I guess I don't have it in here. I guess I'll pull that. It's 40. There it is. Survey. There it is. So here's an example of one that's been done to the fullest. This is a site near our office. It was flown with both LiDAR and photogrammetry, just like we did before. And I extracted not only the 2D data, but 3D catenary lines. You can see the tin there. You can see the lines that are tools for extracting catenaries. There's the ground. I extracted both top and back a curb and top a curb. These are all 3D feature lines that were built into this drawing, all exported out. So the idea is collecting your data, using the tools available to you. There are, whether you use Pix4D Survey or you use LP360 or you use Trimble Business Center, the process is very similar, and we can help you along. If you're interested in this technology and data, you can ask for a demonstration of this directed data or the direct, hey, we're interested in this workflow, or I have these two programs. What can I do with it? Contact your sales representative at Seiler. Don't forget to follow and like our blog. It's www.seiler-ds.com/blog. I'll provide a link to that in the follow-up email, as well as to the link of the recording of this video, as well as the other video I mentioned using the recap photogrammetry software. If anybody has any questions, we'll go just an additional 5 minutes. I don't see any hands. I didn't look at the chat here. I don't see anything in the chat. But if anybody has any questions, please feel free to type in the chat. Otherwise, we'll give it a couple more minutes. Lauren, did you have anything you'd like to add?
I don't. Everything looked great, Mark.
Okay, thank you very much. Thank you, everybody, for attending. And it's a lot to cover in an hour. I tried to keep it as simple, but try to get in some detail. Again, if you have any desires to see a demo or want some more information on what we've shown, please give us a call or contact our blog. There's a request form on there. You can contact me directly at cadtechnical@seilerints.com. That goes to the entire design solutions technical support team. Or you can contact me directly at mschnesk, that's MSCHNESK, at seilerinst.com. Thank you very much for coming, everybody. I hope you have a pleasant rest of the day. We'll be repeating this webinar in a month or so. If you're interested in signing up for that one for a follow-up, I'll probably have a little more refined data by that time. Thank you, everyone, for coming. Have a great afternoon. Stop sharing and stop recording.